Even if you're going relatively quick,
Give a stragglers a little bit of time to get in.
so it's like for the next one, let's try to make it 1 year.
That's okay. What we need to have is an AP person.
The trick is not doing side projects.
Yeah.
Okay. Well, I think we will get started. Bob came in for a set. There we go. Okay. It's my pleasure to introduce Shane Visaga and her seminar today. Shane got her MS at the Manila University in Manila, Philippines in 2021. During her master's work, she was able to participate in the NASA CampX2 field campaign as a weather forecaster, and that's when she met Bob Holtz, which sort of begins her journey eventually to Wisconsin. After getting her master's, she was a research associate at the Manila Observatory, where she did work in energy, climate, and weather forecasts in the Philippines. In 2023, she came to UW-Madison as a graduate student. She's being advised by myself and Bob Holtz. And last year, she was awarded the NSF NCAR Ralph Cicerone Fellow Award, which is a 2-year award. She spent last summer there, and that's actually a lot of her PhD work. But today, she's going to be talking about her MS research on the impacts of cirrus clouds on the planetary boundary layer height in Manila. So take it away, Shane.
Thank you, Brad. Want to check, can you hear me okay from the back? Good. All right, good afternoon, everyone. And as Brad introduced, we will be talking about the PBL height. And I am interested in looking at how cirrus clouds affect the PBL height. PBL stands for, right here, planetary boundary layer. And that is defined as this lowest part of the free troposphere that is directly influenced by the presence of the Earth's surface. For the study, it's focused and it was done in Metro Manila, and we used a very unique data set from the High Spectral Resolution Lidar. And I would like to start by establishing the significance of the PBL height measurements and why should we care about it. So among many applications, PBL height modulates air quality. So for example, in this picture, especially over urban environments, this picture is from Metro Manila. This inefficient combustion public utility vehicles is how most people in this densely populated area go around the city. And this traffic is a major contributor to this black suit that we see in typical morning skylines in the city. And with the PBL height later in the day, when the volume gets larger, that helps improve the air quality because there's a larger volume of air when you mix that constant emissions from the traffic in the city. Another application that most of us might be more interested in is the PBL height measurements are very valuable in evaluating model representations of the PBL, and that has implications for how we can improve simulations, especially over polluted cities. Let's look closer into the PBL structure in this diagram, and here we have the height in the y-axis and the time in the x-axis. This goes from midnight to sunrise, sunset, and then back to midnight again. And as we see here, we have different labels for the different parts of the PBL structure. At nighttime, we have a nighttime stable boundary layer close to the surface, and on top of that, there's a residual layer sitting on top of that. And this configuration transforms or changed into a daytime convective boundary layer. What happens is at sunrise, so as the downwelling solar radiation warms up the surface, that generates thermals that rise from the surface, and so the daytime convective boundary layer is characterized by this turbulent mixing. And in this example, that grows throughout the day as more energy is in the surface from the sun. And it grows up to around 1,500 meters in this example, and that is what we would call the PBL height. And then at nighttime, by sunset, that radiative input is cut off. That also immediately shuts down the turbulent mixing, and then we're back to the nighttime stable boundary layer. And the residue characteristics on top of this is what the residual layer is. But focusing on this daytime convective boundary layer, we notice that it is highly influenced by this downwelling solar radiation, and that is what driving the PBL growth. And there are many factors that can modulate that downwelling solar radiation, including clouds. In this diagram, we have two types of clouds. First, for low clouds. We know that for low clouds, they decrease the amount of incoming shortwave that reaches the surface, and that would lead to the PBL to not grow as deep. But for my research, I'm interested in understanding what these high clouds are, how are they affecting the PBL, because these high thin ice cirrus clouds are semi-transparent to the incoming shortwave, and we want to explore that and its effect on the PBL. Why exactly? Because cirrus clouds, in some studies, they've looked into how they modulate the downwelling solar radiation, but also the very interesting part is because it's maximum frequency over the tropics. This image is from the Calypso data, and the green shading over here around the tropics is where it is highest maximum during daytime. And if we look at the color scale, that means it's around 50% of the day we have cirrus covering us. And I encircled here the maritime continent because that is the region that I am interested in. And we can explore those tropical cirrus and its radiative impacts on the PBL using ground-based observations. Specifically from CAMPEX 2019, it was based in the Philippines. It's an observation campaign that focused on the coupling of tropical convection and radiation. And as part of CAMPEX, that is how I learned about UW-Madison. The UW-Madison SSEC High Spectral Resolution Lidar, or the HSRL, was deployed at Manila Observatory. That's a long-term data set from 2019 to 2020. And this picture is showing us this green laser beam. That's actually the HSRL measuring and quantifying the clouds and the aerosols in the Manila atmosphere. And as you notice, this picture, we can clearly see that green laser beam, and it's because this was taken at New Year's Eve. So with the New Year's Eve revelries, the atmosphere is so scattering from the pollution, and that allows us to see this. But in cleaner days, it's not as visible. So for this data set, it is a very unique high resolution and long-term data set, especially for a data poor region like us. And with this, we can look at both the frequent tropical cirrus, and it is in a very unique tropical urban environment. So just going back to this picture to emphasize that location is an urban polluted PBL, and with the HSRL data, we can actually track until what height that pollution is, and we can track that throughout the day. Here's an example of what the HSRL data looks like, and I labeled the interesting features for this example day on October 3rd. So this picture is showing us on the y-axis is the altitude. This is from the surface up to 10 kilometers. And on the x-axis, we have the time. This is 8 a.m. local time until 12 p.m. local time. Starting at the surface, we have this green signal that has like some fluctuations on top of it. And we see it starts really low near the surface, but it's slowly growing and reach up to around 1.5 kilometers at 12 p.m. And that is actually the signal from the aerosol within the PBL. It's around 10 to the minus 6 per meters to radian of the backscatter at 532 nanometers. And we see this persistent, almost like stable layers that persist throughout the day, and those possibly are from nighttime. Some of that around 1 kilometer, they get entrained into the PBL later on, so that's also an interesting thing to look at. But the one I want to highlight here is how we see this cirrus clouds that is present for almost the entire morning. And so my interest is, how do these cirrus impact the downwelling solar radiation that would reach the surface, and how would that impact the growth of this PBL? Which brings me to my research question: can we observe a correlation between the cirrus optical depth and the PBL height, or the PBLH, using a multi-year observation data set? And another question from that is, how do cirrus clouds influence the PBLH? My working hypothesis is there should be a relationship between the cirrus optical depth and the PBLH, because the cirrus modulates downwelling solar radiation, which directly influences the PBL. So I'm interested in doing an observation analysis, and the three main measurements that I need are measurements of the cirrus, the PBL height, and the downwelling solar radiation. And in this next slide, I'm showing the co-located instruments and the Manila Observatory study site that we had from 2019 to 2020. And over this building that I marked as, because we call that the solar building, is where we had the HSRL set up. So from this instrument, we will be getting the cirrus in aerosol measurements. And it's around 83 meters away from this other building where we had our roof deck with more instruments. We had an all-sky camera, weather station, and a couple of radiometers, including the broadband pyranometer, which is right here, and that will give us the total downwelling solar radiation. And I want to focus on talking about this instrument and the pyranometer, and say something about their field of view. So for different instruments, for example, for the pyranometer, it has a hemispherical view or measurement, meaning when it measures, it can see the entire sky. Sorry. And so to visualize that, here's an example of another hemispherical measurement. This is from the all-sky camera, and we can see, it can see the entire sky. And we have here two pictures, one from the morning, one from the afternoon. The morning, we see some thin cirrus right here. At 2 p.m., definitely optically thicker clouds right there. And we remember when I was talking about the LiDAR earlier, it is a zenith point measurement. And so if you think about that in the context of this hemispherical view, it is one point at that hemispherical view of the pyranometer. And this pictures definitely shows there is some cloud heterogeneity that we won't be able to capture with this HSRL data that I will be looking at. However, the good thing is I can do comparisons of these measurements, and I see that with the HSRL data, it tells us that it corresponds to that image, that there's some cirrus right there, and we see that at 2 p.m. right here, more attenuating cirrus, and we see that it is definitely optically thicker in this image. And the advantage of using the HSRL data is it tells us where in the vertical is the cirrus base and the cirrus tops are, and we can take advantage of that. Another thing that is like a limitation for my work is we have to consider which type of cases do we want to look at. So for a very complex tropical site, we definitely have a lot of precipitation and very complex atmosphere cases. So I only look at these types of cases that I call no-rain days. What that means is I look at days without precipitation. So I use the weather station to look at the rainfall to filter that out. And with these type of cases, we see that we can see the evolution of the PBL, but also since there is no signal attenuation for the LiDAR, we can clearly see up to 10 kilometers, and we can definitely quantify the cirrus clouds for the day as compared to these complex cases to the right, there's so much going on. So again, we have the aerosols within the PBL, but we see these red spots on top of that. So if you look at the color scale, those are higher backscatter values, and those are actually the signal for the low clouds. And once the LiDAR encounters the low cloud, it gets attenuated, and you see in this image, it becomes like black, because that means it's no data or we're attenuated. So we don't know what's going on above these low clouds or above these rain features that we see here as well. So to make it clear, I am limiting myself to these no rain days, even though I'm looking at a long-term data set for the whole year. And with that, I'll spend some time talking about how did we do the detection for the Cirrus and the PBL height. All right. For the HSRL that we've been talking about, the HSRL technique can spectrally discriminate between the particle and the molecular scattering. What that means is it allows us to resolve thin aerosol layers and the clouds, and it has a couple of measurements. So far, I've been showing images of the atmosphere through the LiDAR with this type of measurements, the backscatter. And so in this example from December 4, 2019, again, we have here the height, which is from the surface up to 20 kilometers, and this is the time in BTC. And we can identify, as I've been doing earlier, these are the aerosols within the PBL. Here we have the water low clouds on top of that, and we have this Cirrus signature at around 30 kilometers and above. And another measurement of the HSRL is this depolarization. What it does is it gives us information about the shape of the particles. So low depolarization values, so in this color scale, it goes from 0 to 45%. When it's on the lower end of the scale, these are spherical particles. And when we look at these high values, these are non-spherical particles. So let's try to compare these images. Near the surface, we see that we have these low values of depolarization, indicating that these aerosols and the water clouds that we see near the surface are spherical, and we know that for water clouds, we expect it to be spherical particles. In contrast, the Cirrus clouds that we see here in the backscatter, when we look at its depolarization, we see that its high values, around greater than 27% usually, and we expect this because ice clouds are non-spherical, and so this becomes an indicator for us on finding the Cirrus. So what I do is I use these two measurements and look for signals, so I will be able to identify the Cirrus feature and the aerosol features to be able to track the PBL height. Let's start with the Cirrus detection. This image is a 2D histogram wherein I take all the data from above 7 kilometers, and we expect the Cirrus clouds to be about that height. And here we have the depolarization on the y-axis and the backscatter on the x-axis. And I encircled here and labeled letter A, which is what corresponds to the Cirrus feature. As we expect, it has high backscatter, larger than 10 to the minus 6 per meters per radian, and it has large depolarization because the ice clouds are non-spherical particles. And because this is it's like the first step for detecting the Cirrus, but we want to make sure we have quality Cirrus detection, and so I use this detection algorithm that was developed here by Magano et al. 2020. And this is better quality because we now account for good signal to noise ratio, and that would allow us to properly quantify the optical depth of the Cirrus. What that means, so in this example from December 17, so we see at some point around 15 kilometers, there are time steps wherein we see this white, which is just meaning we don't have data for those heights. It's because the cirrus that we encounter there are attenuating the signal. We don't want to look at these time steps because we cannot fully quantify the optical depth of that cirrus, so we wanted to make sure that we can tell its top and base heights to be able to have that reliable optical depth value. So with this case, I'll show an example of the cirrus that we detected. This is the same day, December 17, and the colors are the backscatter from this case earlier that we are looking at, and the darker colors at the top and the base are just indicating the bounds of this cirrus, and we apply that filtering to the optical depth measurement from the extinction, and so we can get the optical depth of that cirrus for every time step for the whole year. And what I do is, so as we see these colors here, now we have a different color scale. This is for optical depth that is from 0 to 1.5, its unit less. And then we classify these cirrus clouds, and so in literature it's common to have it as thin or opaque. So thin cirrus is when the optical depth tau is less than 0.3, and then if it's 0.3 to 3, we call them opaque cirrus. So those will be the classifications that I'll be talking about in the results later. So after the cirrus detection, I also have to do the PBL height detection. And now we have a similar HSRL image. This is altitude in the y-axis, but now we're zooming into surface up to only 3 kilometers. And in the x-axis, we have here almost an entire day from 6 a.m. to 5 p.m. Okay, for this example, we see these very nice fluctuations on top of that aerosol green signal, which is what we have as the well-mixed aerosol within the PBL. And those fluctuations that we see on top of them is actually the updrafts and downdrafts on top of the PBL. And we are able to resolve that because the HSRL has a very high temporal resolution of 32nd and high vertical resolution of 30 meters. And we also see here how it can resolve these stable aerosol layers, even here with the lower backscatter values, and see how we can trace the fluctuation on these layers as well later in the day. So with this, I'm interested in this aerosols within the PBL, and I do the same 2D histogram, but now I'm focusing on only using the data below 3 kilometers. And as encircled here, so again, we have a deep polarization versus backscatter, and we see in this 2D histogram, we now have identified 3 features. And in this next slide, we show what these are actually representing. So B is for the aerosols, C are the water cloud features, and D is precipitation. Okay, so B and C, as we see here, they're both low depolarization values. And to recall, that means spherical particles. So the aerosols within the PBL and the water clouds are both low depolarization. And to be able to draw a line and distinguish between them, we take advantage of knowing that water is very scattering, so it would have a higher backscatter value. And from literature, we can use a threshold to be able to draw that line and remove those water cloud features in the data set to be able to use only the aerosols for tracking the height. Another thing is that I want to talk about a little is this precipitation signal. As we see, it has higher depolarization value, but it's also like a line wherein the backscatter increases with the depolarization, and this is from literature because of an increase in the backscatter when we have larger spherical particles from rain. But again, my interest is having a water cloud free data, so I only look at the aerosol signals. And with that, having the water cloud free data, I applied a maximum temporal variance in the aerosol backscatter. And the physical meaning of this is we expect the well-mixed aerosols in the PBL to be distinct from the free troposphere. And so what I did is for every minute of the aerosol backscatter, I look at the next 4 time steps and take the variance to find the height where that is maximum and assume that the variance is from the alternating updrafts and downdrafts on top of the PBL. And in air quality studies, this is also called the mixed layer height, but for my talk, I'll be using the PBL height curve. So in this figure, I'm showing an example of the retrieval. So the thin line, black line here, is showing the 1 minute result for the PBL height after applying this method. And I took moving average just for visualization purposes, and that is the thick black line that we see here. So with this, we can see that at 9:30 in the morning, the PBL height is around 500 meters, and that triples in volume later in the day, reaching around 1.5 kilometers. Okay, so from the methodology, we applied that for the whole year, and now I will present the key results from that. All right, starting with Cirrus statistics. So here we have the seasonal distribution for Cirrus optical depth house. So this goes from 0 to 1 in this plot, and we have December to November for this one. And the box plots are showing us the 10th and 90th percentile. We have the median right here, and I also plotted the seasonal mean as the red cross marks. And the colors at the background serves as a guidance on the bounds for the 2 types of cirrus, which is thin and opaque cirrus. So first observation here, we see that for all of these box plots, so we span both kinds of cirrus from thin to opaque, meaning that we can observe both kinds of cirrus throughout the year. And very interesting to see here is how these mean values are a lot higher than the median for all of these seasons. And also we see that the upper tails are a lot longer than the lower tails. In comparison to the median, so what it tells us is that most of our observation for the cirrus are around the thin cirrus, so we have the highest frequency of these kinds of cirrus. But these part of the figure tells us that we have extreme values of opaque cirrus cases that is pulling that mean and this upper tail for the box plot. And when we compare across the seasons, the mean and the tails for June to November are higher than the December to May. And this is primarily due to the generating mechanisms of where these cirrus are coming from. So from June to November, this is the wet, moist monsoon in our region. So, and that transitions to the typhoon season, which are generating this optically thicker cirrus from June to November. As comparison for December to May, these is usually our drier season in this region. So we keep that in mind, the cirrus seasonality. And now I will show the PBL height statistics. We have here the PBL height in the y-axis and the local time in the x-axis. So I have 2 curves. I took an average for December to May, and that is shown by the blue curve. And our June to November average is in red right here. And for those who are interested, the shadows are showing the minimum and maximum values. The key result that I wanted to show here is how we see this difference in these 2 seasons. So for June to November, we have a lot lower PBL height almost for the entire day, only reaches around 1,200 meters as compared to the drier season, which reaches around 1,500 meters. So the main takeaway for putting these results together here is that when the monsoon season to typhoon season is happening, that is when we have optically thicker cirrus clouds. And as the cirrus optical depth gets higher, this leads to a lower PBL height average. And this is telling us that there is a negative correlation between the two in the seasonal timescale. My next question from that is, do we also see a correlation in the daily timescale? So we looked at the days that I used to generate that seasonal distributions earlier, and now we get a daily cirrus optical depth mean that's in the x-axis, and the PBL height daily maximum, which is in the y-axis, and every point here is a daily value. And just adding a simple linear regression here, that is telling us there is generally the PBL height maximum is decreasing as our cirrus optical depth tau is increasing. So for those who cannot see it, the Pearson R value for this simple linear regression is minus 0.46. I also want to mention that the times when we observe these lowest PBLH maximum days are all from June to November. And we observe the highest PBLH max days during the warmest months from March to May. So far from this, we can tell, okay, there's some correlation on both the seasonal and the daily timescale, but when do these cirrus clouds occur the most within the day? And so let's do that in this next slide. Now we have 3 plots, one for morning, one for midday, and afternoon. This is showing us the PBL height distribution for different sky conditions. So I have here clear sky, thin cirrus, and opaque cirrus. Starting with the morning, so let's compare the red cross marks, which are the averages. In the morning, we see that from clear sky to opaque cirrus, we see a decreasing trend in the PBL height. When we go to midday, so this is again going from clear sky cases to opaque cirrus cases, there's not really a difference that we're seeing there. And then in the afternoon, we're kind of close to the morning result, wherein the clear and thin are almost equal, but the opaque cirrus is giving us a lower PBL height average. So if we think about it, it looks like the timing of the cirrus cloud matters. We're in at morning and at the afternoon, and those are the times of the day when the solar zenith angle is larger. So if we have a cirrus cloud and the solar zenith angle is large, once the ray of the sun goes through the cloud, that's a longer optical path, and that seems to be, that effective thickness of the cirrus seems to show us an effect on the PBL height. And literature supports this in a study in 2011 where they did radiative transfer modeling of observed cirrus. For different optical thicknesses of the cirrus, they noticed that the timing when the cirrus happens in the day, that has an impact on the effect on the downwelling solar radiation. This next section looks into why are we seeing a correlation, or in physical terms, how does the cirrus optical depth affect the PBL height? And for this analysis, we'll be focusing on using the pyranometer measurements. And so that's the SPN1 pyranometer. It's measuring the total downwelling solar radiation, but it can also give us the diffuse and the direct component. So the direct component depends on the time of the day with respect to the solar zenith angle, and the diffuse component is from the scattering of the atmosphere. That would include the aerosols and the clouds. And so the F total and the diffuse part are measured by that instrument, and then we can calculate the direct component. But I want to focus now on this quantity that we will be looking at. So this is including the air mass factor or the effective thickness of the atmosphere. So when I talk about F total scale, that's a scaled version of the downwelling solar radiation. Okay, for this result and figure, we have 4 curves, and we'll slowly walk through it. The gray curve is for the clear sky cases, and then I have the low cloud cases in brown, and I have the 2 types of cirrus. The thin is in orange, and the opaque is in green. We include this clear sky and low cloud curves to serve as reference, or like the extremes, to better appreciate the cirrus impact on the downwelling solar radiation, or the F total scale in this plot. We also compare these values for different times of the day in terms of the solar zenith angle. So what I did is I binned the values every 10 degrees, so that goes from 0 to 90 degrees. So 90 degrees, that is when the sun is at the horizon, or sunset, or sunrise. Okay, so first thing from this figure, for all of these curves, generally they have high values at noontime, and that decreases as the solar zenith angle decreases. Now, when we look at the clear sky, when compared to the other curves, it always has, at least here, it always has the largest downwelling solar radiation that it allows to reach the surface, and that would empower the PBL to go deeper. As compared to the low clouds, which is at the lower end of this figure, these low clouds leave less of that downwelling solar radiation to reach the surface. And in between them are the 2 types of cirrus and the cases that we have. What we see when we compare them is the green, or the optically thicker cirrus clouds, leaves less downwelling solar radiation than the thin cirrus cases. So to interpret that, the thin cirrus provides more energy available to the surface to warm up and help the PBL to grow deeper. And from that, from here, we will try to put it all together. And to recall, the hypothesis is the cirrus optical depth is related to the PBL height, mainly because that's bridged by how they are related to the downwelling solar radiation. So we go back to the scatter plot showing the daily values. So we have the cirrus tau, or cirrus optical depth mean, on the x-axis for these 3 plots. Then we want to know the dependence of these 3 things. This first one is the downwelling solar radiation. Next is the direct beam fraction, or the T dir, and the diffuse fraction, or the F diffuse. We also color the daily points based on the PBL height maximum. So yellow shades are the high PBLH days, blue shades are the low PBL height days. Focusing on the encircled ones, which are the high PBL height days, we observe them when we have low cirrus optical thickness, and that leads to high downwelling solar radiation with a high direct beam fraction, and that can be interpreted as more direct heating of the surface, and it has a low diffuse fraction. Now, looking at the same plots, but now focusing on the low PBL height days in blue right here as encircled, we observe the low PBL height days when we have thicker cirrus around greater than 0.3, or the opaque cirrus types, and they correspond to and lead to lower downwelling solar radiation with lower direct beam fraction and a high diffuse fraction. This high diffuse fraction makes sense because as you have optically thicker cirrus clouds, those are more scattering. Another way to look at that is I try to summarize it with this proposed mechanism flowchart. And this is specifically for this observation analysis that we did over Metro Manila. So if we have a given cloud cover, for example, we have clear sky to low Cirrus optical depth. This leads to high solar radiation reaching the surface, and we've seen that from the observation data that we have. That leads to high surface heating or warmer surface that generates high sensible heat flux, and that would propel the PBL height to be higher. So far, we also saw in the data, the observation, the PBL height values, but we didn't really prove or show observations for this part. They're not available, but we take advantage of our reanalysis dataset called MERA2 and get that grid cell for the study site. And this figure is showing us the PBL height from the HSRL that we detected and the MERA2 reanalysis sensible heat flux on the x-axis. The colors are the PBL height values just to be consistent with the other figures. But what we see here is when we have low sensible heat flux, that's when the PBL height is low. When we have high sensible heat flux, that's also when we have the high PBL height. And this one has a higher Pearson correlation coefficient of R equals 0.83. So in summary, going back to the research question and our answers to that, can we observe a correlation between the Cirrus optical depth and the PBL height using a multi-year observation data set? Yes, the HSRL data that we use shows the correlation between the two on both the seasonal and daily time scale, and we also see that the timing within the day of the Cirrus also matters. How do cirrus clouds influence the PBLH? So what happens as we observe is the cirrus decreases the downwelling solar radiation, and this in turn leads to less sensible heat flux that we look at using the MERA2 analysis, and that leads to a lower PBL height as we observe from the HSRL measurements. For future work, it would be ideal to have additional measurements, especially the sensible and the latent heat flux measurements, and more high-resolution cloud-resolving models to be able to actually pin down that relative importance of the cirrus radiative effects on the PBL growth. Other studies also do radiative transfer modeling after knowing the optical thickness of the cirrus. Also start thinking about other forcing mechanisms, especially the surface, because the soil moisture and the surface properties, that's more strongly coupled with what's happening in the PBL. And also thinking about stability, because I am working under the assumption that it's a convective boundary layer, but as we know at daytime there are different stabilities that can occur as well. And as I mentioned in the significance, thinking about how the PBL height impacts air quality, and this is more of my current interest right now. Okay, let's give a slide. I want to end with a thank you slide. This is for my previous colleagues in Manila Observatory and Ateneo de Manila University. These are my panel who work with me. And these images below, just want to mention something. This was the HSRL when it was deployed by Ilya, and these are the Manila Observatory colleagues who helped with that. And that is how I got my MS from this data set. And also, this is a picture from Campex when Bob, who's now my advisor, this is the first time I learned about the HSRL data. And now I'm still working with that. And this is a picture from the Campex during the campaign. It's a picture with the NASA P3 that did the measurements of the convection and radiation in 2019. And with that, open the floor for questions.
So go back to,
Yeah.
so Gemma,
Yes.
she got her PhD here.
Yeah,
And
so,
why don't you give a little history there?
yeah, I'd be happy to share that. So Dr. Gemma, who passed away while I was doing my master's, she was my original research advisor, and she was actually here in UW-Madison for her postdoc with Professor John Foley before she went back to the Philippines and did her research there, inspiring more scientists like me to pursue further studies. All right.
questions, and we'll take questions from students first. Yes.
I have a kind of naive question. I think it was really cool the way that you showed the seasonality of the high Cirrus clouds and the impacts of that. I was just wondering, like, how much does the radiation change over the course of the year in this region? Does that have an effect, and is that effect, like, is that a big effect relative to the clouds, or is it a small effect relative to the differences in the clouds?
Thanks, Arban. That's a good question. I actually look at the seasonality of the downwalling solar radiation or the total irradiance, and when you take averages, you can't really see a difference on that. And it's on a daily basis, you can definitely tell that it's very localized on the cloud cover.
Yes.
Hey Shane, great presentation. I have a naive question as well about the low clouds and its seasonality. So you said that you get rid of the data if it has a low-lying cloud, and I wonder whether once you do that, your final usable data, do they have similar sample sizes between seasons, or it gets affected or not?
Yes, so I think I want to show very quickly this extra plot. This is the seasonality for, that's perfect. This is the seasonality of the low cloud, and it's definitely highest at that June to November time when we have that wet monsoon and typhoon season. And that limits me with, I think I only have 20 days for that time of the year. And I would say I tried my best to isolate the low cloud effect, but it's not perfect.
I have two questions. First one being, if I remember correctly, your low cloud detection is rather shallow, 3 kilometers or so. Or my bad, the PBL height, 3 kilometers. And you're trying to isolate when there's scenes of only just cirrus. Do you ever find that there's mid-level clouds that are caught in your detection algorithm? You might see the influence of mid-level clouds.
Okay. So when we implement the Cirrus cloud detection from 7 kilometers and above, and I remember there are cases when it's almost like hard to differentiate them, especially these series are coming from like anvils of cumulonimbus. And usually when you have those middle clouds, they get really optically thick, and so they're attenuated, and so they usually don't get included.
Okay. And then my second question was, if you're looking within a certain day, are you able to detect how much growth in the PBL height you can observe as soon as a cirrus cloud is present, like a lagged response in the PBL height? Or is that too difficult with the HSRL?
That's a great question. I get this question a lot, and I still haven't pinned that down because it's the challenge for I'm showing the distributions and as a summary figure because it's hard for me to get these very comprehensive cases to look at that. But knowing that when I was talking about that immediate shutdown of the turbulent mixing when there's cloud cover, it should be very instant, like almost instantaneous response.
Yes.
Hi, great presentation. I'm wondering if you saw any patterns in the intensity of the HSRL backscattering of aerosols based on the PBL height. Like, were you able to see them disperse a little bit with the higher PBL?
Okay, like a higher backscatter with larger amount of aerosols, you mean?
Yeah, just how do you see any differences in the aerosol concentration based on the height of the boundary layer?
Yes. So remember that diurnal profile that I was talking about, and how when the PBL goes deeper later, if you have constant emissions from the sources, that actually dilutes the concentration of the aerosols. And I tried comparing so we have this surface particulate matter measurements that you can compare with the integrated aerosol backscatter that serves as a tracer for the amount of pollution, and it has almost a really good linear relationship. And when I look at that integrated aerosol tracer from the LiDAR, it really nicely, the values, the pollution increases when I look at that with a lower PBL height day or time of the day.
That's great. Great.
In the event where you have a residual layer on top of your growing stable layer, is there some sort of response to the depth of the mixed layer in the next day based on the height of the residual layer in the previous day?
Could you repeat what's the effect
On the PBL height on the day after the residual layer is starting to diffuse away. I'm wondering if there's a response to how deep that residual layer is to the growth of the PBL in the next day.
I haven't looked at that, but like for example, in this case, I would think some of that is definitely residual from the local emissions from the PBL, but very interesting in our region because the city is in between water bodies and a mountain, and so there's also that influence of that air coming from the mountains, and so why we're getting even up to 5 kilometers, we have this stable aerosol layers.
I guess I'd point out that these are actually very low backscatter amounts. These are very tenuous sort of layers. They just stand out in HSRL because it has such high precision.
It's amazing.
And sensitivity.
It's just amazing.
Yes, John.
Shane, really great work. That is really interesting and well presented. I guess I don't know off the top of my head, so maybe you do, and you alluded to it in future work type questions. Could you take your March, April, May days and filter them for, I don't know what Manila's climatology is, but how many times do you get consecutive days without rain? So that there's absolutely no water on the surface in some fraction of those days versus days where an inch of rain fell the day before. Do you see a substantial difference in the depth eventually of the boundary layer without regard for cirrus clouds, or just timing when you're trying to evaporate water first?
You're interested at the warmest months?
Yeah, the ones that are driest too, so that you might have the most frequent consecutive days without rain or something. I don't know if that ever happens in Manila.
Because the PBL is defined as its response in the time scales of in an hour or less. So I haven't really thought about thinking about it on a longer time scale.
Yeah.
But especially that this is an urban city location, it definitely gets really warm from that from the type of surface that we have, and that, as I mentioned, the surface is more directly coupled to the PBL, and with consecutive hot days, which is also concerned for us for like heat waves. That I would say that would be interesting to look at.
I guess because I'm imagining a rainy day could clean out the air in a metro area like Manila, but then 2 warm days in a row could do it too, because you might build a deeper boundary layer and it gets ventilated. So I don't know which one's better, and that could be an interesting thing to explore if you have the data.
It's a good question, though.
Yes, yes.
Because we definitely can tell you whether it's precipitating or not. Like,
Yeah,
that's
yeah.
the data set. Like,
Yeah.
that's straightforward to pull out.
Yeah.
So.
But you might not have a big enough sample left. I'm wondering.
Yeah,
know,
the
'cause
sampling is tricky, but it's an interesting take on. Yeah, I mean, this data set is unique and very powerful. There's a lot of low-hanging fruit here to play with. So.
Yeah, it's really great.
Yeah.
Great work.
It's a long-term record.
Yeah, I also just wanted to say, really great presentation, and I know nothing about this, so I was excited to understand a little bit, so you were very clear. And I was just wondering whether there is, whether you can comment on interannual variability like most people you show this for 1 year, right? And this sort of seasonal. Is it very regular every year the same signal, or do you have years where you just don't have as much cirrus clouds?
So I can speak about the Cirrus interannual variability because I was able to proceed. So when I did my master's 3 years ago, I only focused on 2019 as I'm trying to extend this to 2020. I do see the similar seasonality in the Cirrus when I compare these 2 years. I cannot say that for the PBL height because I still need to implement that. It's kind of a rigorous methodology that I have to work on for a big part of my master's. But yeah, for the seasonality of the Cirrus, very highly tied to that monsoon. To that monsoon. And of course, there's interannual variability in that yeah.
What about what about interannual variability in the overall aerosol loading, not just from Manila, but from the whole maritime continent?
Okay, I have a question for my advisor.
Well, let me put it another way. Was the Campex period a period of high aerosol loading, or I want you to talk a little bit about fire influences.
Yes, I'm definitely going there. So the interesting thing with Campex, here I highlighted that it's focused on convection and radiation specifically for this talk, but we also captured that biomass burning from Indonesia area, and we are downwind of that during this time of the year. And this is one of the highest CO emissions because it's a drier year. And so I'm not in that picture, but remember that picture where we have that aerosol layers on top of the PBL? We are interested in looking at differentiating and knowing from our air pollution, what's the contribution of the local emissions and the transport from the maritime continent fires. And so depending on the burning year, if we are influenced by that. But because I look at traffic data, hourly traffic data for 1 month, and it's surprising that it's almost constant, like 2,000 vehicles per hour. So it looks like it's almost, we can assume it's constant emissions throughout the day. And the PBL helps with that. But also, I didn't talk here about the winds. So depending on the winds, if that's cleaning the area or if it's stagnating the pollution. So there's so many factors.
Hi. You had a slide where you were comparing the PBL height to the Cirrus optical depth at different times of day. So for example, for the midday plot, is that cases where there weren't also morning Cirrus clouds? Like there was only Cirrus clouds in the midday?
Oh, yeah, that's, I see where you're going there. That's a good question. I only did a simple temporal grouping here. So now I'm not sure if, like for example, this clear sky cases, if there was Cirrus before that when I did the grouping, but that's a good thought.
Yeah, because it'd be interesting too if it's Cirrus all day, and because that kind of implies that it would grow really rapidly and then die away really rapidly. Could it still be the same height, just overall, early and late, it's lower?
Yeah, good point. I'll take note of that. Thank you.
I can ask him this part.
Yeah, because you'll be at the gap. Go ahead.
Just a quick follow-up to that. Do you, like, whenever there is or isn't a Cirrus, is there any sort of, like, do you do anything to, like, make that fuzzy, like, immediately before or after? Or is it, like, because, what did you say the temporal resolution was? It's super high.
Yeah, so for the original
Yeah.
data set, it's 30 seconds.
Yeah, so, like, if there are Cirrus clouds, but then you don't detect it for, like, 10 minutes, but then they come back, do you count all of that as Cirrus, or do you count those 10 minutes in between as clear sky, and then it comes back to Cirrus?
So I do not have a filter for like what's happening before and after. Right
Okay.
now, this is again the simple For
Yeah.
time step, I group them as clear sky and opaque. So
Okay.
that might be affecting this result that we're seeing in the midday.
Okay, great questions. Let's give Shane another round.